So this is, I got a notification the meeting's being recorded. Okay. So this work some of the work that I'm presenting today is going to be featured in a paper that's going to be in the archive, hopefully within the next week or so. So be on the lookout for that. So just general overview. So I am part of the NANOGrav collaboration, North American Nanohertz Observatory for Gravitational Waves. And as the name suggests, we are looking for nanohertz frequency gravitational waves. And the way we are doing this is via an array of pulsars distributed throughout the galaxy. You could sort of think of it as a mini armed LIGO. And instead of lasers, we use the signals from pulsars, and we time the arrival times of these pulses and look for time delays that would correspond with the gravitational wave signal in our data. So the most recent data release, which is the upcoming, actually I think it's already out, the 12.5-year data release. So it has 47 millisecond pulsars with up to 12.5 years of data. We add new pulsars all the time because more pulsars will always give us greater sensitivity, even if the precision of those pulsars is not necessarily as good as some pulsars we already have in our array. Just more pulsars will always give us more sensitivity overall. And so we're currently down to sub-microsecond precision for some of these pulsars, which is really important because we think we need 100 nanosecond precision, give or take, for detections. And after 12.5 years, we're already starting to see a common red noise process between our pulsars and our data. We can't claim detection yet, but we're fairly close, we think, just because we're starting to see these strong correlations. So be on the lookout in the next couple of years for more conclusive results on that front. So what I work on in the collaboration is correcting for delays from the interstellar medium. So I look for what are called scattering delays. So basically, if you have the pulsar signal, it passes through an ionized medium, in this case, the interstellar medium, and interacts with free electrons. And these interactions with free electrons will cause deviations in path length. And so we get signals arriving at different times at the Earth and our telescopes based off of the interactions between the free electrons. So we get these delays. Some work in my collaboration has been examining the effects of these delays to an extent. So Lean 11 in 2016 looked at the 9-year data set, and it showed that a lot of our pulsars have 10 nanosecond precision, 10 nanosecond level scattering delays. So that may not seem like a lot, even in context with the 100 nanosecond precision needed for gravitational wave detection, but we have some pulsars that do have, much larger scattering delays that we're having difficulty fully resolving based on our resolution at the current stage. So more exploration into this is needed. And we don't currently actually include scattering in our timing models. And I feel like at this stage where we're so close to making a detection, this level of precision is sort of necessitates the need for correcting for scattering delays. We also have effects like dispersion measure, which you can think of as more large scale overall effects along the line of sight. So dispersion measure, it's the free electron number density over the line of sight, effectively integrated over the line of sight. So that also is sort of a large base ISM effect, but we already correct for that, and we at each epoch, and so that's already been accounted for in our data. But this smaller scattering effect is not really included in our timing models as of right now. So what we do to examine these is we look at the power at each epoch in frequency and time, and what we get are these plots here, the top plots, which are the sort of orangish yellow plots. These are dynamic spectra, and so these tell us these basically are plots of intensity, or I guess flux density, and so they tell us the degree of scattering we see in pulsars in frequency and time. So the brighter patches that we see that are sort of like little filaments, those are scintills. And so based on the length in frequency and time of these scintills, we can determine the scattering delay in our pulsars. So if we look at the left plot, so the second plot from the bottom, or sorry, second plot from the top, is a 2D autocorrelation function. And so if we take a 2D Gaussian of the center of that, we get the bottom two plots. So these are autocorrelation functions in frequency and in time. And we can use, for example, the bottommost plot, so that's the autocorrelation function in frequency space, to determine the scattering delay. So we get a what's called a scintillation bandwidth, which is effectively the width of a scintilla in frequency. I mean, in the same way that the second to the bottom plot, which has the delta t sub d, that's the scintillation time scale. So that's the width of the scintilla effectively in time. So, but the scintillation bandwidth is effectively to within a couple of constants. Effectively, it's the inverse of the scattering delay. So the wider the scintilla, the less strong the scattering effect is. And so with that, we are able to infer scattering delays as a function of frequency. So one thing to note here is that because of the inverse relation of scintillation bandwidth and scattering delay, we will, as we get to higher and higher scattering delays, we'll have smaller and smaller scintills or narrower scintills. And so that means that we're actually less sensitive to more highly scattered delays, which is kind of unfortunate because those are the ones that are going to affect our data the most. And that's going to be something we explore later on. So yeah, that's the general idea of how we extract scattering delays, at least in the paper that I will hopefully be submitting soon. So yeah, I'm showing a few more of these plots just to give an idea of the resolution issues that I was discussing. So on the left is a dynamic spectra. It's not fully resolved in time, but it's fully resolved in frequency. And so we have scintills that are fully observable. That's from, I realized I didn't have the pulsar that's B1855 plus 09. Whereas on the right-hand side, we have 1937 plus 21, which is the first millisecond pulsar ever discovered. It's a very bright pulsar. It's also very highly scattered. It has a high DM relative to most of our pulsars. It's further away than most pulsars as well, or most of our pulsars. And so while, I should mention the bottom plots too. So the bottom plots are the secondary spectra. So these are the Fourier transforms of the dynamic spectrum or dynamic spectra, which are the top plots. And so what those basically can tell us is what sort of power we expect at different delays. So the amount of power that is being resolved at different delays. And the reason that I showed the secondary spectra is that if we collapse those along frequency, we can look at how resolved in power these dynamic spectra are, and that will indicate to us whether or not we are fully resolving their scintills. So while some of these scintills in 1937's dynamic spectrum look resolved, there are a lot of narrow scintills on the left that could be questionable in terms of resolution. So if we collapse them along their center frequency and look at how the power drops off, we can see that the power in 1855, does drop off. So we are fully resolving its spectrum in terms of power, meaning that its scintills are fully resolved and we're actually accurately measuring the amount of scattering. Whereas in 1937, the power does not really change at all. So we're not really, it's likely that we're not fully resolving the effects from the scattering delay for that pulsar. What else I could talk about here? So you may notice that the scintills are not even in length or even in width in some cases. So scattering delay is proportional to frequency to the minus 4.4, meaning that if we measure over a wide enough band, we might not get scintills of even width. And so when we measure, if we're claiming so typically what we do is we measure one scattering delay measurement for each observation. But since we use wide bands, we have to stretch them in order to account for this this frequency dependent effect. And I'll get into this a little bit later, but if we stretch with the correct power and frequency, so if frequency to the minus 4.4 is actually correct, then what we should be seeing in these plots is evenly sized intervals all across these bands. And you can probably already glean this from the right-hand plot on 1937, but at least for some of the epochs, it does not seem like stretching to that power is correct. But we'll explore that in a little bit. So a general overview. So in this paper, we recovered scattering information from 28 of these 47 pulsars. A big issue with a lot of them is we don't either have the resolution currently. So we use 1.5 megahertz channels, which corresponds to a scattering delay of about 150 nanoseconds. So some of our pulsars are more highly scattered than that, and so we can't fully resolve their scintils, so we don't know how much we're underestimating their scattering delays by. But a lot of the pulsars are in like the 10 nanosecond regime, so anywhere from 1 to maybe 50 or 60 nanoseconds. As I just mentioned, we ran into resolution limits with some of these pulsars, but and of course this is kind of problematic because these are the pulsars where our where we're running into these are pulsars where the scattering effects are the strongest, and so they're the most problematic for our sensitivity. And just I'll sort of go over this in I think next slide, but there is if we look at the scattering delay over time, we see a level of variability that may be intrinsic to line of sight rather than observing frequency, which is kind of interesting because we might expect more variability based on the frequency, but it's more likely to be related to the pulsar's dispersion measure or its overall distance. So these are just two examples of pulsars looking at their scattering delays over time. So we have 1944 and 1713 at 1500 megahertz, and we're showing scattering delays on top, their flux densities in the middle, and their dispersion measure, or the change in dispersion measure on the bottom. So it's clearly it seems like it's a random process, at least in terms of how scattering delays follow. There's not really any clear trend. It's just some sort of random deviation as we vary from epoch to epoch. So, but we can still look for correlations between scattering delay and other effects like flux density and dispersion measure. In theory, we would expect there to be some correlations, but in our paper, we don't really find any. This could just be because we have, in many cases, more epochs of flux density or dispersion measure than we do of scattering delay. But it's sort of an open question at this point why we don't see that. I mean, there is some level of correlation, but it's sort of in agreement with other papers that have come out before in terms of the amount of correlation. But given what we expect from theoretical predictions, we don't see that level of correlation yet. However, we do find general agreements with scattering delay models. So if we look at how scattering delay changes as a function of dispersion measure or distance, or at least according to theoretical models that are, I guess they're not really so these are models that are based off of fits to various pulsars that have history of scattering delay measurements. So our pulsars do follow along those trends more or less, which is good until we get to lower DMs, but that may just be resolution limits on our part. So, and I should mention, we have a couple of pulsars with arrows. Those represent upper limits. So these are some of the more highly scattered pulsars. These are pulsars that where we run into resolution limits. So we got 1937 as an example. That's probably one of the further out ones. So it's got a DM of around 70. And then on the right, so this is a comparison with NA2001, which is an electron density model. So it looks at the levels of electron number density at different points in the galaxy. It was developed by Jim Cordes and Joe Lazio in 2001. And so our measurements generally agree with the predictions found in that model. So that's good. So that means that assumptions that we have about the electron density structure in our galaxy, or at least within a couple of kiloparsecs of Earth, are fairly accurate. So that's promising. Okay. And I mentioned earlier, if we believe the scaling laws for how scattering delay changes as a function of frequency, then we'd based on the assumption of a uniform, or what's called a Kolmogorov medium, then we would expect scattering delay to be dependent by frequency as to the minus 4.4. But if we break apart given dynamic spectra and measure the linear slope as a function of frequency across those bands, then we can look at the scaling index and see whether or not how we're stretching these dynamic spectra is actually in agreement with this minus 4.4 assumption. And what we found in the vast majority of our pulsars is that actually in all of our pulsars is that we find shallower indices, which is interesting, but it's in agreement with a lot of what other groups have found. So Lena Levin, who did a scattering delay analysis on the 9-year data set for NANOGrav, also found shallower scaling indices than are expected. A number of other groups have also found shallower scaling indices than are expected. So it's not entirely surprising. I mean, it is surprising from a theoretical perspective, but it's not surprising in terms of what other groups have found. But there are a couple of explanations. I mean, one is just we need better resolution on some of these pulsars. If we have better resolution, then the slopes we measure across the band might be steeper. So we might expect that we might be underestimating delays at higher frequencies or lower frequencies and overestimating at higher frequencies based on resolution. And so that might steepen the indices that we find. But it's a little bit of an open question, at least. Why it's not quite as steep as we'd expect. But there is a little bit of variability over time. So, I guess within errors for some of these epochs, you could argue that it's sort of an agreement, but it's the level of shallowness is kind of it's a little bit unexpected. So because of these resolution issues and because of just our need to incorporate scattering delays directly into our timing pipeline, we're turning to what's called cyclic spectroscopy. So we, in this method, look at information from the phase of our signal as opposed to the amplitude, which is what the autocorrelation function method with the dynamic spectra use. So if we look at the sort of signals from the ISM, the interstellar medium, we can if we look at time shifts as a function of different pulses from our pulsars, if we look at the slope of the phase differences between those signals, then we can infer a time shift, and then we can relate that to the period of our signal to get a scattering delay. And so if we think of the signal from the interstellar medium as this impulse response function that can be described by this this one-sided exponential, and we can find what's called the cyclic spectrum by convolving that signal with the pulsar signal, so the pulsar pulse. It's quite a bit more computationally intensive, but it can provide much finer frequency resolution, which is going to be super important for highly scattered pulsars. I have only just started working on this stuff in the past couple months. So if you're really interested in the mathematical background of it, you should look at the Paul Demarest 2011 paper for much more details on the mathematical derivation of cyclic spectroscopy and what it looks for. So we wanted to compare the effectiveness of cyclic spectroscopy with traditional methods like we just looked at in the previous slides. So we simulated these impulse response functions with some noise from the interstellar medium and compared the recovery of the cyclic spectrum phase method with autocorrelation. So the left plot is a one-dimensional version of a dynamic spectrum. And so we can simulate those and then determine an autocorrelation function from that. So what you're seeing on the right is the corresponding autocorrelation function to this 1D dynamic spectrum plot with two fits. So typically we've just assumed Gaussian fits in our ACF plots for the paper for the previous slides for the paper, just because it's a good approximation. But if we're thinking in terms of Fourier analysis, if the impulse response function from the interstellar medium is a one-sided exponential, then the more correct way of fitting for this autocorrelation function would be with a Lorentzian, since they're Fourier transforms of each other. So we looked at both of these methods and then compared them with the simulated the cyclic spectroscopy fit. So in theory, the scattering delay should be the centroid of this impulse response function. So then what we're doing is we're simulating a bunch of impulse response functions and comparing the centroid to the delay derived from the cyclic spectrum phase and from the exponential, and the Lorentzian and Gaussian fits to the autocorrelation function. So these are some results from those simulations. So there's some weird vertical blue lines. That's just because at low enough signal to noise, so these plots are looking at signal to noise ratio, and at low enough signal to noise ratio for some of the analyses, it just blows up. So I tried to plot these so that they just they all have the same y-axis scaling. So what we're looking at here are so there are about 300 points in each of these plots. Each point represents the average of 1,000 simulations of some random draw of around a 1 microsecond signal from the ISM. And so basically the takeaway from this is that well, first off, if we just compare the Lorentzian and Gaussian fits to the autocorrelation function, we can see that the Lorentzian being the more accurate representation, or the more accurate and more reflective choice for a fit to the autocorrelation function generally is a better fit. We see some bias introduced by the Gaussian, so it's not actually picking up on the correct scattering delay, and it's also even within error. But the more interesting thing is if you look at the Lorentzian fit compared to the fit from the cyclic spectrum phase, not only they're both in agreement with the expected injected scattering delay, but the average error from the cyclic spectrum phase approach is much more precise. So that already sort of gives credence to the cyclic spectroscopy method as being more precise and more reliable. But the interesting thing is, if we look at the correlations, we can see that there's basically no correlation if we look at all 1,000 instances of a given signal to noise ratio. The cyclic spectrum phase versus the centroid, the actual centroid from the impulse response function, is almost perfectly correlated. So not only is it performing better than either the Lorentzian or Gaussian fits to the autocorrelation function on average, but for an epoch-to-epoch basis, the cyclic spectroscopy approach is far and away the better option. So this is kind of significant because the autocorrelation function dynamic spectrum approach has been what's been used for a few decades. So if this is able to be implemented in real time on our NANOGrav pulsars, then we could significantly we can detect scattering delays with precision, but also just incredible accuracy over individual epochs. So that's kind of exciting. You know, it's yeah. So basically, this also shows that we can assume that the cyclic spectrum, the phase derived scattering delay from the cyclic spectrum is basically the equivalent of just measuring the centroid of the impulse response function from the interstellar medium. So that's pretty exciting. So I will mention that these simulations are just looking at signals from the ISM, so we have not introduced the pulse signal yet. That's going to be our next. That's going to be what we're doing next. So we're going to be convolving a pulse signal with the envelope from the impulse response function, and then doing similar simulations with that. So, but we don't expect that the results will change very much. We expect similar sort of trends as we see in these plots. So in general, we find that cyclic spectroscopy is probably what's going to be necessary if we hope to effectively measure scattering delays from highly scattered pulsars. Currently, a lot of our pulsars are in the 10 nanosecond regime, especially some of our more precise timers. So it's not the biggest, it's not the most urgent point, but if we really want to conclusively confirm gravitational wave detection, then it's going to be really important to implement this in the near future. So we hope to implement this real-time cyclic spectroscopy pipeline into our timing pipeline within the coming months, which will allow for instant scattering delay detection and correction. And more importantly, we'll be able to resolve these highly scattered pulsars, which are going to be more important for precision in the near future. I spoke a bit faster than I thought, but that's all I had at this point. So I guess thank you so much for having me, and I'll take questions if there are any.
I've got excuse me, this is Jay Lockman. I've got a couple.
Okay.
When you say that the pulsar is not included in your simulations, do you mean you're using an impulse for the actual pulse shape?
Yeah. So, so in those simulations, we're just using the impulse response function. Typically, if we're thinking physically, the actual signal we would get is the pulsar pulse convolved with the impulse response function of the interstellar medium. Our simulations currently just have the impulse response function.
Yeah. Could you back up a slide where you show the autocorrelation function?
This one? Yeah.
Yes. Would you talk about the negative side lobes, if I'm using the phrase correctly?
Yeah. Interesting. So actually, you mean where it goes negative, or?
Yeah, around 200 minus 300 plus or minus. Yeah.
Honestly, I'm not sure if I can give a good explanation for those. I just when I made this plot, I just normalized it and centered it at 0. So in reality, you might not have negative lobes like that. I just wanted to center it at 0 to make it look good. I don't really have any more explanation on that. I'm sorry.
That's okay. And finally, you showed a plot of pulsar flux over time and for individual pulses. Yeah, that's it. And so you've got order of magnitude changes in the flux density of some of these. And that's averaged over how many pulses typically?
So observations are, well, we have, let's see, so 1713 would be a green bank. I think we have 10-second subintegrations, and observations are about 30 minutes in length.
So each point is 30 minutes?
Yeah.
Yeah, okay. And was that one of the things you said was puzzling that was change in flux density was not correlating with any interstellar
Yeah,
effects?
we'd expect. I mean, yeah, theoretical predictions suggest that flux density should be correlated with scattering delay to some degree, but we didn't really find any, which could just be we don't have enough. I mean, there are many more flux density observations here than we have scattering delay measurements, which is just because we couldn't resolve scintills on each day we observed. So it could be that if we had one scattering delay measurement for every single flux density observation, it could be that there's a correlation in there, but we just haven't found it.
Okay, thanks.
Yeah.
All right, any other questions for our speaker? So I guess I had one. A few slides back, you showed the profile being fit with a Lorentzian and a Gaussian.
Yeah.
And so why would you, I guess, expect a Gaussian better fit compared to the, or a Lorentzian better fit compared to the Gaussian?
Yeah.
And have you tried like a Voigt profile or anything like that?
So the reason we expect a Lorentzian to be the best fit is because an impulse response function is generally expected to be a one-sided exponential, and the Fourier transform of a one-sided exponential is a Lorentzian. That's basically it.
Okay.
No, we haven't tried any other profiles, but it could be that they fit better. I just couldn't think of a physical reason to do that.
Okay. So was the Gaussian showed there just to show the comparison between the two then?
Yeah. A lot of previous, for some reason it seemed in the previous NANOGrav paper, they used Gaussians to fit the pulses. So for consistency, not to fit the autocorrelation functions, and so just for consistency, we also looked at that as well. But the Lorentzian is the physically most reasonable choice.
All right, any other final questions? All right, I guess we will conclude there, so that way you have time to get to your next class at 1.
Thank you.
We will be back next week. Our speaker next week is Ashley Barnes, who is a postdoc at Bonn in Germany, and he will tell us about his recent paper on star formation. So we'll see you all then.
Thank you, Jacob.
Thanks for having me.
Yeah, thanks. Bye.